So we'll see.
The entire city of Cahokia is designed around sky worship.
I remember an early trip past Cahokia. My father was a truck driver, and I occasionally, as a little kid, 6 or 7, I would go with him, and we would drive past it. I remember feeling like, wait a minute, like, what's this doing here? What is this?
That drive past the mounds sparked a career for archaeologist Tim Pocketot. His research suggests that Cahokia, like Teotihuacan, is laid out on a celestial blueprint.
The mounds are positioned in various ways, to reference something. They're not arbitrarily, randomly placed. They never just dump dirt.
Tim and his team are looking for evidence of that celestial blueprint just west of Cahokia's largest mound. They use a gradiometer, an instrument that detects holes where posts once stood.
I'm seeing very quiet readings, and then it jumps up again, so it could be consistent with post holes.
The original posts have rotted away, but new ones have been erected in their place. They form a ring with one post in the middle. It's known as Woodhenge.
Woodhenge is a large ring of sizable cedar posts. And if you look from across that post to the perimeter post. You could watch the sun on the horizon rise and set, and you'd know when the solstices were.
Just like the sun disk paintings in the Amazon, Woodhenge is a solar calendar. It can be used to determine when to plant and harvest, and when to gather for ceremonies.
This is a big ritual ground. Inside the circle is some kind of sacred space, and you'd go there for certain ceremonial events.
Like the Sun Pyramid in Teotihuacan, the location of Woodhenge is precisely aligned. On the equinox, the sun rises to the east, directly in front of Monk's Mound, Cahokia's largest earthen pyramid.
On a major event, let's say an autumn feast tied to the equinox, there'd be thousands of people on the move, coming in from all directions.
Artifacts from Cahokia show just how far pilgrims traveled. This carved stone pipe was found 500 miles away. It depicts a player of an ancient Native American game called chunky. In one hand, he holds a spear, which was thrown at a rolling stone disc. Hundreds of chunky stones have been excavated throughout the United States.
Cahokia-style chunky stones start showing up hundreds of miles away. So the thought may be that you play against people, either you make friends or you resolve disputes instead of going to war, you play chunky.
The chunky stones in the rise of Cahokia date to 1100 to 1400, a time of unusual peace throughout the Mississippi region.
Well, hello everyone. This is Scott Roberts from Explore Scientific and the Explore Alliance, and it's our 41st episode of How Do You Know? And in this particular episode, Dr. Barth talks about measuring time. Now, he and I spent a little bit of time talking about it before we started broadcasting, but it is just a really interesting aspect of knowledge of the human race. And so Daniel will go to the fringes of kind of where it all started and where it's at today. So Daniel, thanks for coming on yet again for another episode of How Do You Know?
Hey there, Scott. Welcome, everybody. And I love that video. I've been to Cahokia.
Oh, have you
I've been
really?
to see the mounds. It was, oh God, it's more than 30 years ago now, but it reminds me of a place I should go back to.
Yeah. Maybe you want to
Cahokia
build one, like right out here in the Explore Scientific parking lot or something,
The amazing thing, I've also been down to Toltec Mounds near Little Rock. And I was there as a boy, and I was able to, when you were still able to climb the hill. You're not allowed to climb up the hills anymore. But when I was a boy, we could go climb all over that and run all over it. It was fun. And we went to Cahokia and got to see the mounds. It was before they ever built that henge, or reconstructed the henge, I should say. But it's a fascinating thing, and this idea keeps recurring. There was an article I was looking for, I couldn't find it. The coast of Peru, there's a series of masonry structures, and it makes this sawtooth along a ridge, and it too marks the solstices and equinoxes precisely. And this idea of some sort of a henge, or a position where you could watch the sun move north to south as it rises, is really fascinating. My home here on Round Mountain in the Ozarks, I have this view to the east across the valley. And so in the mornings, I can get up and watch the sunrise, and I see it move north and south across the ridge, about a couple of kilometers distant. And I'm fascinated by this. And saw this article about leap seconds, and the Earth's rotation is slowing down or speeding up, I guess. Anyway, I saw this and I thought, that would make a nice little show note thing And then I started reading and thinking and doing some more research, and I realized, no, this is worthy of an entire hour's discussion, and it should be a lot of fun.
Agreed.
One of our issues here, Scott, of course, is that astronomy is such an ancient science. We've seen this before. We've talked about, what's the definition of the moon? And we worked through, and I showed everybody the working definition of a moon that I use in my classes and work. And one of the problems when you say things like moon and planet and second and time and month is these ideas are, 50, 80, 100,000 years old and more. They extend back before language, before history. These ideas are so ancient. And as our understanding evolves, oftentimes our language has trouble keeping pace with our understanding. And we have these terms that we use, which we've used since time immemorial. It sounds like a corny phrase, but true. And we look at this and we say, wow, well, we've been using the term moon for, golly, at least 15 millennia. It goes back to very ancient times, and there are words for the moon, I'm sure, which are far older than that, which we do not know. When we take a look at clay tablets with constellations on them, some of the older constellations that we recognize today, constellations of the zodiac, we have some of these constellation records that date back 10, 12, 15 millennia. 15,000 years ago, you're talking, we talked about the destruction of Tal el-Hammam, Sodom, the biblical city of Sodom, destroyed by an impact strike. And you're like, that was 3,700 years ago. And so some of these clay tablets predated this stuff by 10,000 years, predated the Tel Hammam civilization by millennia. And you're going, wow, your brain kind of explodes with the duration of it. And we have this issue today. We need to reconcile ancient methods. Our language is often rooted in ancient ideas with modern science and our improved understanding and definition of this. And it continues to be challenging. It's something that astronomers struggle with. And when we talk about, what's the big deal, leap second, blah, blah. Well, just to give you two examples, GPS system, right? GPS system doesn't work unless you can keep time to a 10,000th of a second and adjust relativistically for the high speed of travel of the satellites. Unless you know relativity, it doesn't work. The best we could get is a few hundred meters. We could never have GPS. We could never have Google Maps. And they had stuff like that before, which were called inertial maps. They would actually measure how far your wheels rolled on the pavement and make an update. And you would roll up to somewhere and say, no, I'm here. And the map would make a little adjustment. You would go ahead and roll. Are your tires really the right size? Have you had tread wear? All these things affected it. And now we've bypassed all of that because we have satellites. But the satellites don't work unless you understand relativity and you can keep track of time to a 10,000th of a second.
Crazy.
So we look at that. What about financial transactions? Every financial transaction in the world has a unique timestamp. Did you buy it before the price went up, after the price went down? When did you make this purchase? And it isn't just enough to have a rubber stamp or a, do you remember, Scott, they used to have rubber stamps with clocks built into them?
With clocks built in? No, but I've seen it
Yes.
where, the
They had
time and
rubber
everything,
stamps.
you roll the
No.
rubber stamp to get the
I'm
numbers right.
actually talking about a clock where the face of the clock was a rubber stamp. And
No.
it was a wind-up clock.
No.
And I've seen these in
That is cool.
offices in schools where a student would come in, you arrived at this time, and they would
Yeah,
take the
you're now
clock
in
stamp,
detention. Boom.
and they would
right?
stamp it, and it would stamp a little clock on the face, and it would show the exact hour. We see some of these things with stamps in plastic goods, where a stamp is pressed in that records the date and time when something was molded or made. We see
It's
this.
true. And a lot of the serial numbers on our products are indeed done like that. We know
Yes.
what day they were done, and a lot of details actually thrown into the serial
Indeed.
number. Yeah.
So what about leap seconds? leaping
Yeah,
forward,
what about
leaping
them?
back. Well, if you spring forward with a leap second, then there's a second of time that's missing. There could be no transactions during this time.
Hmm.
But if you fall back, then the same second repeats itself. How do you uniquely identify that second when it repeated? And of course, there's been other times when we've joggled the calendars and things like that. So we continue to recognize this. I think probably the moon and the sun easily our first clocks. And the little video we had at the beginning, they show the henges.
Yeah.
Henge calendars date back probably 5,000 to 10,000 years. And again, Stonehenge, we think, was a copy of a wooden structure which was there before. And they probably renewed the wooden structure a number of times before they built it in stone. We know the stone dates from about 3,500 years ago. The wooden structures may have gone back another millennia or two. So this idea of a henge, sun circles, the Hopi and the Navajo and the southwestern United States have sun circles. There are things like this. The Aborigines in Australia and New Guinea and New Zealand had them. The Maya and the Inca in South America, other Native American tribes had them. Teotihuacan in central Mexico, the Olmec in Mexico had them. And so this idea is something that almost all civilizations develop. We've talked about this, Scott, and I've said for a long time, the three pillars of human civilization, astronomy, sanitation, and agriculture. Astronomy allows you to keep a calendar, which makes it's a life or death thing. If you're going from a nomadic society to an agrarian society, the calendar becomes a life and death matter. Plant at the right time, harvest at the right time, or your children starve to death.
Right.
Literally, the calendar is a life and death thing. And of course, agriculture allows you to stay in one place and occupy territory rather than moving through it. And then, of course, sanitation, if you're going to stay in one place, you got to handle the waste or you will die. You put bacteria on a plate and they overgrow the medium and they die from overpopulation.
People did die.
People did die.
They did
Oh,
die.
yes.
Yeah.
Oh, yes. Even you go to modern, relatively modern London, the 1600s cholera outbreaks because the water system was unsanitary and tens of thousands died. So these things, and people say, calendars, what's the big deal? My watch has a calendar on it. Well, yeah, okay, bub, sure. But in ancient times for these people, planting and harvesting, and these would have been closely tied with their religious ceremonies. And you've got to do it right. You've got to know the right days, and being able to tell what day it is was a life or death matter. And these henges were used for that. With a properly set up henge, you can set up markers and you can say, here's the marker for the winter solstice, the summer solstice. Here's the marker for the equinox. We've won a great battle. Let's put up another post here. Let's remember when the sun is on top of this post, we won a great victory over the tribe over the hill and took over their territory. This is a great religious celebration because we saw a comet in the sky. And so we erect a post the next morning and we say, this is the spot when we worship that every year. And Easter, which is coming up soon, is a lunar holiday. It is the Sunday following the first full moon after the vernal equinox. And you go, what? When you tell people how Easter is determined, what day does it fall on? And you say, oh yes, it's an astronomical event. It's the first Sunday after the vernal equinox. And you go, wow, wait, you mean they had to be astronomers before they could have a holiday like this? Yes. And the Jewish religion has holidays like this. The Chinese ancient cultural calendar has holidays like this. And all the native societies and cultures in America and North and South America and the cultures throughout Africa had things like this, where the important days for celebrations were based on astronomy. And so these calendars are really important and how we keep time. And then we kind of take a jump into the modern, or at least the historical era, where we have written records. And we start looking at the Babylonians. And the Babylonians said, the Earth goes around the sun in 365, and they were quite accurate. The Babylonians and the Mayan calendar, they had eclipse calendars which would go out centuries, and they were right on the number. The accuracy of the Mayan calendar in terms of the length of the year was not exceeded until the 1920s or 30s. It was amazingly accurate. The Babylonians were amazing mathematicians. And they looked at this and said, ooh, 365 and a quarter, that's kind of sloppy. Let's call it 360. And so they decided 360 days was a year. What do we do with these other, the audience has noticed the clock has stopped on my wall. You're right, friends and neighbors.
Leave that up to Mike Wiesner.
I have one of these radio-controlled atomic clocks, and indeed the battery has run out, and it's a clock, but I have a special battery for it. So Amazon will save me. My clock will function again. That clock is, I don't know, 20, whenever, it's quite old. It's 27 years old.
As an official host of How Do You Know, Daniel, I will gift you a Explore Scientific atomic wall clock. So.
Well, thank you, and I will display it proudly. So this is hilarious. So the Babylonians, back to ancient people, didn't have trouble with their atomic clocks. The Babylonians said, let's say the year is 360 days, and they had this 5 to 6 day holiday. Oh, it's the non-calendar holiday. And this idea, people look at this and say, really, they did that? But they did this, the Romans did this. People talk about, how are we going to keep time on Mars with its 24-hour and 37-minute day? So various science fiction authors have talked about what they would do. The idea of a time slip where clocks would just stop for 37 minutes. They would be programmed to stop for 37 minutes and then resume again. But you get into problems with that, because if you stop for 37 minutes every day, you find this problem with your clock not keeping pace with the sun. That's the whole idea between spring forward, fall back, and adjusting our time, is to keep our clocks relatively consistent with the sun. Should be noon, of course, is an astronomical time. It's when the sun crosses the meridian.
Sure.
And sailors at sea, as Walter Winchell used to say, hello, Mr. and Mrs. America and all the ships at sea. Well, these sailors at sea would use sextants, and the marking of longitude was taken on latitude was taken rather on the day when, boom, the sun crosses the meridian. It's now noon, and we can tell precisely the sun is at its zenith for the day, and we can get the latitude precisely and record our position in the ship's log. So we still have these fudgy things. And you talk about that thing on Mars, it's not such a weird issue. Other people, me included, have talked about the idea of what some people refer to as a Google smear or a smeared second. The idea that if Mars is 24 hours and 37 Earth minutes, that you could make the second on Mars, the Martian second, just a fraction longer than an Earth second. And it's not very much. So that Mars solar day becomes, in fact, divided into 24 hours. And each hour on Mars would be something like 1 minute and 20 seconds longer than an hour on Earth. But the clocks would tick slower. So then it would still, on the local clock, it would still say it's an hour. 5 p.m. would still be afternoon. When the sun crosses the meridian at noon, it would all make sense. But if you had an Earth watch, it wouldn't keep time with Mars time. Mm-hmm. Of course, unless it's a smartwatch, and then you just say, oh, my location is Mars, and the internal computer adjusts the ticking of the clock on the display on the face. but a mechanical watch would not keep time. And this has been a feature in mystery, science fiction stories, and all sorts of things over time. So the Babylonians say, oh, 360 days. Why did they do that? Well, it turns out that if you're really into math, and the Babylonians were really into math, and if math is important to you, and to the Babylonians, it was a sacred thing. Like the Pythagoreans, the Babylonians said, oh, what about the Mars dial? Yes, the sundials? Yeah, sundials on Mars would, of course, keep perfect Martian time because it's based on the rotation rate of the planet. So you could take an Earth sundial to Mars and it would keep correct time, at least as accurate as it would on Earth, because it's based on the pendulum, if you will, is the rotation of the planet and the passage of the sun through the sky. And Mars tilt isn't very different either. It's 25.5 degrees. We're 23 and a third, something like that. So the tilt is very similar. A sundial would work perfectly on Mars. You'd have to just adjust it a little bit in terms of its angle and position and line it up with true north, and boom, you'd be solid. So this 360 degree, one of the things they like is because 360 has more factors than almost any other relatively small number. It can be divided by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30, which means you've got lots of ways to nicely divide up the circle. So we know that if we divide it up into 12, we get the familiar 15-degree hour, but you can divide it up by 5 and get, you can get bigger or smaller slices. It's very easy to divide up the circle. And it makes the math relatively easy. Although when we compare it to the Arabic base 10 system, it seems awful. But we have to realize, we have to remember, timekeeping for astronomers, even up through Galileo's day and Kepler's day, and up into the time of Newton, astronomy was based on Babylonian math. It was based on sexagesimal, or base 60. And we think about, have you ever tried to done one of those math problems, friends, where somebody says, where the teacher says, okay, Billy plays checkers for 1 5/7 hours. How many minutes and seconds is that? And so you have to do all of these crazy base 60 calculations. The astronomers, up through Newton's time, were doing astronomical calculations in sexagesimal base 60 mathematics. All of these in Kepler and Copernicus's day, the astrologers who were doing these ornately complex star charts with the old geocentric model with 90 circles in it. And the 90 circles were all different sizes and they rotated at different rates. And they had different epicycles and all sorts of things. And they were doing all the rotational calculations by hand in base 60, which just fries my bacon. It just makes my head hurt to think about doing all these rotational calculations in base 60 by hand. Just absolutely nuts. And people say, well, why do we do 24 time zones? Why do we do hours of right ascension? Why do we measure things in the sky as so many, degrees, minutes, and seconds of arc? Because the degree, 1/360th of the rotation of the sky, is linked back to the Babylonian calendar. And the idea of an hour is 60 minutes each of 60 seconds. And so we made the degree of arc each of 60 minutes of arc, each minute of arc of 60 seconds of arc. And we still do these calculations today. How far apart is this? And we measure with our hand. Oh, how many degrees is this? How many degrees is that? How many degrees is this? How many degrees is this? And we talk about pinky extended at arm's length, that's 1 degree. Crossed your fist, about 10 degrees. This is about 15 degrees. And so we do all these by hand calculations. I teach students to map the sky even today. And I say, okay, take a standard 30-centimeter ruler and hold it at arm's length. At arm's length, because of the radian and 57.5 centimeters and the average length of the human arm, effectively at arm's length, 1 centimeter arc span on a 30 centimeter ruler equates to 1 degree of arc measured in the sky. And is it accurate for every person? No, because some people's arms are longer, some are shorter. But in fact, if you do it consistently, Scott, and you hold your arm outstretched, and I'm going to hold my arm outstretched here,
Sure.
and so I'm going to go, ooh, I've got my arm outstretched. I'm holding the ruler. Your measured degree of arc with the ruler will always be consistent. You're not growing or shrinking anymore, right? So we teach students to do this, and we say, oh, well, even if there's a multiplier discrepancy between what you measure and what astronomers measure, you can make maps based on this, which are accurate because your measurement is consistent to itself, right? You're not estimating a degree of arc, you're measuring it. Maybe your tool is imperfect, but it's imperfect in the same way every time. And ancient societies measured time, and they had this issue. They weren't necessarily accurate, but they were measuring within a tool which was consistent. We talk about accuracy and precision, precision being repeatability. You can have precision without accuracy, and if you know how far you're off, you can get quite good measurements.
Precision
So,
without accuracy, that's kind of like Hubble's first mirror, right?
oh yes,
Highly precise,
but not accurate. Yes, and I'm sure somewhere, someone, their ears are burning and they are cringing and they don't know
Yeah,
why.
I'm sorry, guys. Yeah. We
Yeah,
fixed
but
it.
no,
We
I'd
fixed it, and it
say the idea that we didn't junk it, that we, the old
Yeah, we fixed
adapt
it.
and overcome.
That's right.
Oh, we've got another technological problem.
Yeah.
Let's solve it. And
I'll tip my hat to Story Musgrave, who heroically went up and made most of that
Installed the
happen.
fix.
So,
and the
but he'll
Congress
tell you it
who
was a
said,
team
yes,
effort.
let's spend another X tens of billions of dollars fixing this. God bless them for having some vision.
Yeah. Well, at least they didn't build 2 of them wrong at twice the price. So
There you go. So we continue to explore this idea of time and calendars. The Roman calendar, which our modern calendar is based on, they had 10 months. They were the original decimal calendar system. And they had 10 months, which gave them 304 days. And they had a 61-day winter siesta. It was non-calendar. And they called it Mercedonius. And it was this time. And you have to realize that with 10 months, the names start to make sense. September, which should be 7th, worked. September was the 7th month. October 8 was the 8th month. And December, decimal was the 10th month. And so the names made sense. And then they added in, they said, ooh, let's add January and February.
Uh-oh.
And they filled out the solar year, and they now had a 355-day calendar. And this idea of Mercedonius was a leap month, which was added every few years. They would have a month of 8 to 10 days that they would just add in to re-zero their calendar with the solar realities of life. Julius Caesar, the first Caesar, and his calendar reform stabilized the length of the months. And you had to have either from 28 to 31. And we got the famous poem, of course, about
who was it during Caesar's time that actually kind of worked on that? Or was it a team of people?
I wasn't able to find any records of who did that, who did the math. And I'm sure they had to have a cadre of astronomers working on this and doing measurements and doing the mathematics. And it was probably there were various philosophical academies at the time. And almost certainly it would have been one of those organizations that undertook this. He also went ahead and say, ooh, let's rename a month for me, actually for my family, the Julii. And so we got July.
Hmm.
And during his civil calendar reform, the astronomers determined the length of the year to be 365.25 days. And so they realized, the solar time is not precisely aligned or a multiple of the Earth's rotation time. And they said, well, we're going to have to juggle the calendar occasionally, but they just kind of left it at that. We leap forward to the 1500s. So we're coming forward 15 centuries. And we know that the leap year, the idea of a leap year was not observed. They knew the Earth was going 365.25 days per year, and they just didn't account for it. So by the time of the mid to late 1580s, it was realized that, gee, our calendar isn't lining up with the solar calendar anymore. Our civil calendar and solar calendar are at odds. There's a story which may be apocryphal that around 1300, church, I've heard the story that it's a church and that it's a crypt. But this church, let's call it a church, was built so that on Easter Day, the sun would shine in through a window and illuminate the altar, stained glass, miracle, beautiful light, sunrise on Easter Day. Well, they realized after a couple hundred years, it wasn't lining up anymore. I suspect it wasn't Easter. I suspect it probably was the winter solstice, which would have been a Christmas miracle. I suspect it wasn't Easter because Easter is a floating holiday. So I think I have to call the buzzer, the BS buzzer on the Easter story. But I think it likely was either an equinox thing or perhaps a winter solstice thing. And they found it wasn't lining up. And so Pope Gregory the 13th set up a commission to do calendar reform. And they went back to the ancient records and they like, oh, look, 365.25 days. Well, let's go ahead and get our best astronomers. And in 1500 and the 1580s, I would be surprised if Galileo were not involved in this somewhere. I can find no record that he was, but he certainly was a well-known mathematical genius who was not out of favor at that time. And unlike later in the early 1600s, when he's in his 70s, this set the clock back 30 years. He's in his 40s. He's at the height of his powers. He's a world famous astronomer and mathematician. I would be stunned if he weren't in on this, measuring the length, the exact length of the year. But I can find no record of it. I can't imagine knowing of somebody like Galileo at the height of his powers in his mid 40s and saying, yeah, let's use a Florentine.
Newton, Galileo, Halley, almost any astronomer worth his salt, would have dabbled in this, I would think.
I would think so. I would think so. There probably were people working on it at a lot of locations and mailing their results by donkey to Rome. In any way, they determined the Earth's calendar, Earth's solar year, 365.2422 days. Not quite 365.25. And so the Gregorians, Pope Gregory did two things. First of all, he basically said, well, we're going to have this new leap year system. Every 4 years, we get an extra day, unless it's a century year, when we don't have one, unless the century year is divisible by 400 when we do. The year 2000 was only the second time since the Gregorian calendar was introduced that a century year indeed had a leap year. It would have occurred in 1600, and then it occurred again in 2000.
Mm-hmm.
And so this system of bouncing around leap years every 4 years, except unless, exception, etc., This is supposed to keep our calendar accurate for some millennia. The other thing they did was they realized, oh, our calendar has been slow. And so they said, and you can imagine the letters went out, right? Everybody's going to get the letter at the same time. And the letter said, gee, we're going to have Thursday, October 4th, and then we're going to have Friday, October 15th.
Okay.
Can you imagine the government today
9 days
saying,
missing. Yeah.
oh, we're just going to skip ahead 11 days.
Or 11. That's right.
And if you have a birthday then in that time span this year, surprise,
Yeah.
everybody celebrate on that Friday.
So-
or if
But
there's
if you're working during those days that aren't there, do you get paid for them?
apparently, I couldn't have committed a crime then, Your Honor. Those days didn't exist.
It didn't even exist. That's right.
I know I used to give my students, back before we had Google and you could just look stuff up,
Right.
I used to give my students a set of trivia questions. And one of them was, what important events happened in Europe between October 4th, 1582 and October 15th, 1582? And the answer is nothing, because those days don't exist. And my students would go, what the heck? So I mean, I read about this and I'm just like, and of course at the time, 1580s, the literacy rate, very small, and business is all records on paper and parchment, and maybe you had a bound book, maybe you didn't. You had a scribe. Literacy, the ability to write was very rare. In the same way, people who wrote were scriveners, from which we get the term scribbler. And so the Pope said it, okay, fine, we just changed the date. So we're messing, and we're not done messing with the calendar, because the way we measure time still changes. So 20th century, 1905, we get relativity. 1919, Eddington says, let's go see an eclipse and see if this hotshot Jewish kid from Switzerland knows what he's about. And they measure the deviation of the star behind the sun during the solar eclipse, which of course requires very high precision, and quantum theory and all sorts of advances in physics in the early 20th century. They're all requiring higher and higher precision in terms of measuring time. When you're talking radioactive decay, measuring half-life, measuring particle collisions, and these sort of things, they're requiring measuring time to 8, 10, 12 decimal places, tiny, tiny billionths and trillionths of a second. And so 1930, Isidore Rabi develops atomic beam resonance. Now, Rabi was a young physicist. His parents immigrated to the United States early in the 20th century. He's not one of the Jewish intellectuals who left during the Nazi purges. He was over here at that time. And he developed this idea that, we can have this atomic beam resonance. And it led to two really important technologies. The first is magnetic resonance imagery. Friends, if you have an MRI on your knee or your back or your elbow or your head or whatever, you benefited from Professor Rabi's, and I'm assuming it's Rabi and it's not Rabbi, because that's a Jewish title. So if somebody knows the pronunciation and I'm in error, please pop into the chat and let me know. But Isidore Rabi develops his magnetic resonance imagery, and he doesn't. Then he said, you know what else? You could use this atomic resonance to make an atomic clock, because the resonances of atomic nuclei are highly precise. And from this idea that atoms could resonate, it was actually after this that we developed quartz clocks. So quartz timekeeping comes in and atomic timekeeping comes in around the same time. Rabi wins the Nobel Prize in 1944 for his atomic beam resonance and the technologies developed therefrom. And so the National Institute for Standards and Technology, NIST, it used to be just the National Institute of Standards, but it's now the National Institute for Standards and Technology. They developed the first atomic clock using ammonia molecules in 1949. I looked up stuff like that, and I have no idea why they settled on ammonia. Perhaps it was easy to purify. It was certainly readily available. I'm certainly, it had its drawbacks. Ammonia is fairly corrosive. It smells really nasty. But basically, it was about 3 years later that they switched to a cesium atom, and they developed a modern cesium clock in 1952. And this becomes the world's time standard in 1952. And the National Center for Time, the National Atomic Clock in Boulder, Colorado, is set up fairly closely after that. And that clock in Boulder sends out a radio time signal. My watch is actually, this is a Citizen EcoDrive radio controlled watch. And this watch actually receives an atomic signal every night at 2 a.m. and it readjusts itself. So it's within 1/100th of a second each day. And each day it realigns itself to the atomic clock. The clock on my wall, which the battery has died, and it's a weird battery, so I don't know if I'm having trouble getting one. That clock also tunes in to the Boulder signal at 2 a.m. and you have to have it in a certain place. None of you have been to my studio here on high atop Round Mountain, but there's a window that looks off to the west in the direction of the atomic clock. And so the radio signal comes from that direction and it reaches my atomic clock up here on the wall and it aligns itself every night at 2 a.m. So we've got this situation where we've got, we've got this great atomic clock, and you can now get broadcast time signals and all of that stuff. Back in the day, and you remember this, Scott, you would be listening to the news and it would say, at the tone, it's 12 noon.
Oh, right. You used to be able to
beep,
call. You could call on the phone.
Oh, yes.
WWV and hear the,
Exactly.
It would make a
You used to be able
tone
to make
once
a
it got
phone
to the
call
top
and
of
get
the
the
hour,
exact
top of
time
the
for your
minute.
watch. Yes, indeed. And the news stations would say, at the tone, it is 2 p.m. Boop. And
Right.
This was an important civil service because everybody didn't have the internet. Everybody didn't have a smartphone, which was automatically synced into the atomic time signal, et cetera, et cetera. So, yay, life is good, life is golden. We don't have any problems now because we have an atomic clock. Let's measure the Earth's rotation really precisely. And it's not consistent.
Oh
no. Now what do we do?
What?
The standard of rotation, the standard of timekeeping throughout human history has been based on a couple of things. The rotation of the Earth for a day, the orbit of the moon for a month,
Okay.
and the orbit of the Earth for the year. And the assumption for literally 100 millennia is that these clocks, these celestial clocks, are perfect.
Kind of goes back to certain individuals and beliefs that the sphere of the sun was perfect and the sphere of the moon was perfect, and so this idea of perfect and
the Pythagorean solids and Kepler's harmony of the spheres, the whole thing.
Find out nothing's perfect.
Wow, it's amazing. Well, and then they get this really accurate clock, and damn it, the Earth isn't keeping time. It's like the old grandfather clock doesn't keep time with my atomic clock watch. So what we've had for a period of time, starting in 1972, we had positive leap seconds where we would go ahead and advance the clock, the atomic clock, 1 second. And we would do that for the same reason we adjust our clocks an hour spring forward, fall back in seasons of the year is because we want our mechanical clocks to keep time with the position of the sun in the sky and the Earth's position going around the sun. So I think it was 72, we had the very first leap second. And the thing is, they did this because Earth's rotation is slowing down. We've talked about this too. We've had this show, if you go back to the show, about tides and eclipses, and we realize the moon is orbiting farther away every year, about a centimeter or two. And in so doing, where does it get the energy to speed up and move to a larger orbit? Well, it steals energies from the Earth's rotation, and the Earth is slowing down. And there's this gravitational transfer of angular momentum from the Earth to the moon. It gives the moon more energy, it rotates, it goes faster in orbit, it expands its orbit, and the Earth, of course, slows down. And we've talked about the idea that over the history of the moon, 4.5 billion years, the Earth's original rotation period would have been about 8 hours. So where now we have a high tide, low tide every 6 hours, back then it would have been, egads, every 2. So you can imagine the moon being much closer, a much higher tide, rushing in miles, rushing back out many miles every 2 hours. It would have been an awful place to be. And so as the Earth's rotation slows down, and it's not consistent, because there are various things that affect how fast the Earth rotates. If you remember back in about 2006, we had this tremendous subduction quake in the Indian Ocean, and the village of Aceh got overwhelmed by this tremendous tsunami. And the Earth, with this big subduction quake, well, guess what? You get this big subduction quake, the Earth's circumference actually shrinks because the Earth's circumference is here, and then it subducts, massive subduction. It actually changes the Earth's circumference and the distribution of mass, and so
Yikes.
changes the Earth's rate of rotation. They were actually able to measure the subduction quake in Fukushima in Japan a few years ago. They're able to measure the effect on the Earth's rotation rate. Because when you have the expansion from mid-Atlantic rift and that sort of thing, you tend to increase. And then, of course, it increases rather steadily, but it decreases from the subduction event quite suddenly and catastrophically. And so these things mess with the Earth's rotation. We also realize that we have large mass concentrations. If you follow geophysical research, you will find that we've detected, there are these very heavy, massive blobs of magma. And we're talking millions of cubic kilometers of material. And the interior of the Earth is neither consistent, nor is it well balanced. And these giant mass concentrations, these mascons, are in motion beneath hundreds and thousands of kilometers beneath the Earth's surface. These things are in motion. The convection currents spin these blobs around like blobs of oil in a lava lamp. And you go, oh my gosh. Well, the real weird thing, since we started doing positive leap seconds in the early 1970s, the last 50 years or so, which takes us back, we've been finding that in fact, the Earth's rotation rate hasn't been slowing down like it should, like gravitational theory and all that predicts that it should. In fact, it's been speeding up. And because it's now speeding up, we don't do leap seconds the way we do leap years. Oh, every 4 years, except on a century. We don't have a schedule like that. We simply measure the Earth's rotation rate in comparison to the atomic clock and say, well, it's time. And a group of scientists on a committee decides, when are we going to do this? When do we schedule it? And do we? And every time before this, the leap seconds have been positive. We've jumped the clock ahead. So we've lost
like fodder for a science fiction novel.
Indeed.
A group of scientists try to decide what's going to happen to the fate of humanity over this these this second that goes by, you know, so.
Precisely right.
Mhm.
Well, with the Earth speeding up now instead of slowing down,
Hmm.
we need a negative leap second.
Hmm.
So we've had spring forward. Now we're going to have fall back. So repeating a second.
Yeah, are we? I mean, has
Nobody's decided yet, but
no
it's
one's
looking
decided,
like
but
that's
they're
going
about to
be the
change
done
things
thing.
again, right?
Well,
Oh, they want to.
they want to, and since 1971, you know, you realize the state of computer technology in 1971, right? Okay, astronauts are still going to the moon with slide rules.
Right.
Okay, all the Apollo rocketry is all built with slide rules. It's not built with computers. There's no computer simulation, anything. They have computers at NASA who are people. And there was that movie just recently. Someone will put it in the chat, I'm sure, about the women who did the calculations for the orbits and all this crazy stuff by hand. Nowadays, we've developed the software for the internet, for financial transactions, for GPS systems. And it's all based on a standard system of time. And these things are able to account for a positive leap second, but none of them are able to account for a negative leap second. What do we do when we repeat a second? Do we call it, you know, 12 o'clock and 23 seconds A, and then 12 o'clock and 23 seconds B? The fact of the matter is none of the computer systems which are in place have the ability to deal with a negative leap second. Do you remember Y2K?
Oh, yeah.
Planes
Yeah,
won't fall out of the sky.
Yeah, and the world was going to come to an end on Y2K.
Oh yeah. I had a good friend who
Mayan calendars were all set.
He said, "Oh, you must
Armageddon was on its
head
way
out into the desert beyond all the freeway intersections in Los Angeles because Y2K is going to come and the traffic is going to immediately go smash. Airplanes will fall out of the sky because we don't know how to deal with a
pacemakers will
4-digit date
stop
stamp instead of a 3-digit date stamp." Well, now we're repeating a second, and again, none of the software. And people are clutching their pearls and throwing their hands in the sky. Then there's a whole other group who says, why do we give a damn? Just keep the atomic clock going because it will take centuries for it to be off even by a minute.
Yeah.
This isn't like Pope Gregory who said, oh my gosh, it's almost 2 weeks off. These special things are almost 2 weeks off from the true solar day. And so can you imagine the first guy who came to the Pope and said, Holy Father, did you know that the sun is not keeping time and on the 21st of December it's no longer lighting up our altar like it's supposed to? Does God not love us anymore? I can't, like the conversation would have been fascinating, both terrible and funny. And maybe that's another book for me. I don't know.
Yeah.
Pope Gregory and the Crisis of Time. But
There's
there are
times
people
to laugh
saying
outside and times to laugh inside, Daniel. So
quite so.
Right.
It would have been serious.
At least chuckle.
Yes. So there's a whole group of people who are now saying, why do we give a damn? It's the same thing with the people who say, why do we shift time back and forth? I hate the idea that people are saying, let's keep daylight savings time. No, let's just set standard time and let it go. I'm old enough to remember, you are too. You remember Nixon's experiment with 2 years of daylight savings time?
I do not remember it. But there was a lot of Nixon stuff I tried to block out. So
I'm going to spew water out my nose now. But in fact,
stories,
yes,
folks. So
when we had the year of daylight savings time in the wintertime, we were getting up in the dark and going to school. And of course, for people who live very far north, this is like, well, what's your problem? Oh, we do this every year. My friends in northern Canada are like, well, yeah, sure. You get up in the dark and you go to school. Of course you do. I have a friend who lives in Alaska and he's like, well, yeah. But keeping standard time, they say, oh, I don't see any reason why we have to have a time shift to keep. And people have said, "Oh, the business argument. Oh, businesses need the business." Well, just shift your business hours. It's summertime, so instead of closing at 6, we're going to close at 7. But everybody says, no, we must, instead of messing with schedules, we must mess with everyone's clock. And then there are
Yes.
states which famously say, I won't do it because we have farmers, and farmers go by the sun and not by your blinkety blinking clock. So it's a wonderful journey. We're still not done. We're still not done. We think, oh, what it must have been like back in Pope Gregory's time. But you know what? We're in those times now. There are people now remote from us, more learned than we are about these issues, who sit and debate things which may or may not affect us. Probably not like we're skipping ahead 11 days, but really for the peasantry at that time, it made no difference. Right? Every 7 days, that's why they had bells on churches. Come to church. They didn't assume anybody was keeping time. The bell was there because the idea was, oh, the learned people at the church, the local parish priest, he kept the calendar for you. He told you when it was Sunday, when it was time to pray. He told you when Lent was coming, when Easter was coming, when Christmas was coming. All these things were kept by the people who knew. And we have the same issue today. So we are still living in this age. And it's fascinating to me how much baggage we carry forward with us because our lovely, wonderful, venerable, ancient science of astronomy is so very, very old. And our language lags a millennia or more behind our technology. We had that program where we showed this whole stack of textbooks and we said, oh, none of these have a definition for the word planet or the word moon. Well, why not? Because it's a very ancient term. And so our language lags a millennia or so behind our technology. Our technology changes so fast. We have a higher percentage of people educated in these sorts of things today than we ever have. And we have so many more things. It's not just some obtuse science experiment with a synchrotron down in the basement of a great university somewhere, but in fact, everybody's cell phone, financial data, 401k, pension accounts, stock trades, all of these things are influenced by the way we keep time. And we're still struggling with, are we going to set up a purely mechanical timekeeping system and say, you know what, the Earth and the sun and the moon no longer matter? And you realize that's exactly what we're struggling with. We have this perfectly nice Cesium clock, which is ridiculously accurate, millionths of a second per year. It's based on fundamental constants in behavior of atomic particles. It's fantastically accurate. Matter of fact, it's so accurate, it's hard to measure how accurate it is. And we look at this and we say, ooh, we've got this situation where now, are we at a point where we're really going to say, you know what, the rotation of the Earth and the sun and the moon, the whole solar lunar calendar doesn't matter to us anymore? And culturally, we're really not ready to let that go. We're really not. We want to know 4th of July happens in the end of summer, that Christmas occurs near the winter solstice. We want to be able to set the date of Easter as the first Sunday following the vernal equinox. And we have culturally these traditions that we've kept since before recorded history. Millennia before recorded history, we've kept these traditions.
Or something like those types of things. That's for very sure.
Yeah.
Certainly as you go to different cultures, different countries around the world, you'll find that they celebrate things differently or whatever.
Yes.
But still, it is revolving around the same kinds of aspects. And I'm with you, Daniel. I think that huge cultural, religious events that crop up every year, definitely helps set our you know, our thinking of time.
Indeed. And Gregory and his learned scholars said, let's set up this system that will keep our calendar accurate and consistent for some millennia. And we know there'll have to be an adjustment again someday, but it will be millennia in the future, and we will leave it to our future ancestors to struggle with that when the
Figure
day
it
comes.
out. Yeah.
I see no reason myself why we cannot have we have Greenwich Mean Time. We could have Cesium Mean Time. Cesium the day. I know that's terrible. I apologize already. We could have this Cesium Standard Time. And if every few years we want to adjust our civil time, or if really we say, you know what, this Cesium clock and our clock, this is going to keep us for a couple of millennia before it's even a few minutes off. So we'll leave that for our distant ancestors. Scientists who need it could use Cesium Standard Time. Everybody else uses the regular calendar with its regular leap years. But when we try to link the past with the future and make things consistent from ancient times to today, that's where we run into trouble. Anyway, there we go. Another exciting show in the bag. And we have episode 50 coming up sometime in the near future. We also have the release of Star Mentor coming up sometime in the near future. So I'm hoping that maybe we can have some sort of if the book is actually out, maybe we can have some sort of a celebration, trivia contest, something. And maybe we can put a copy or two signed by your friend and
We will
narrator.
definitely make that happen. Yeah.
Because I think that would be an exciting way
Sure.
to celebrate the 50 milestone for How Do You Know, and the release of Star Mentor by Springer and Friends in the Patrick Moore Practical Astronomy series. I think that would be wonderful stuff.
It'd be awesome.
So we'll look forward to that. And I got so far down the rabbit hole with this program. Next week's program is going to be a surprise, friends, to Scott and to you, because I don't have a topic for you right now. But it will be interesting, it will be fascinating, and it will be lots of fun. And I want to thank our audience. And any questions before we go that have come up on your chat?
Let's see. Some comments here. Mike Wiesner, who noticed that your clock was stopped on the wall, said, when a solar flare wipes out the electrical grid for a few years, your electronic clocks won't work anymore.
Yeah, we can protect we have good enough predictions for space weather that we actually could protect the grid. It would not be pretty. We would basically be shutting down the grid when the impact of the flare was expected. We can shut down and unplug equipment, and we can protect an awful lot of things from damage. And it's a question of how, because really it's the size of the piece of metal with the strength of the magnetic frequency vibration, which causes the overload, which damages circuits. And so the question becomes, with Earth's magnetic field protecting us, how big a system is going to be damaged, and where do you get something that's small enough? Will my little electric battery operated watch be small enough that it's not going to be affected? How about my car? Is that big enough? So there's a lot of questions, but we could indeed protect ourselves as long as we know it's coming. And right now we have enough warning that we can get a couple of 3 days warning of a massive solar flare and know that we need to protect ourselves. So I have hopes that civilization won't go in the toilet for years.
So I think I will end this program with the fact that you can still dial up WWV on the telephone.
That's what you were doing.
And there it is, top of the minute, right there.
I love it. I love it.
Old,
So,
reliable, almost analog, okay, atomic.
And you're dialing it
clock.
up on a landline, which I just think, yay!
That's right. Yeah, you got to do it on a landline. So that phone number, folks, is 303-499-7111. And if you dial now, you'll get the time. So absolutely free phone call. Well, you'll have to pay the long distance charges, but you'll have to pay WWV. So there you go.
That is wonderful. That is, and there we are, folks. Scott participating in old school time measurement, and it's marvelous. We live in the era of Cesium Standard Time.
Love
Maybe.
it.
All right,
guys.
everybody.
Thank you so
Thank you.
much. Yeah, thank you so much, Daniel. It's wonderful. Great conversation about time and how we are still trying to figure it out. So tomorrow we have Global Star Party. It'll be our 91st Global Star Party. Excuse me, our 90th Global Star Party. And we have one of the really interesting people, and there's going to be many. There's some new ones that are coming on. But let me give you some information about this person. His name, this guy's known as the father of laser-guided adaptive optics. Okay, so all the active optics packages that are on the big telescopes today, this guy is the so-called developer pioneer of it, and his name is oh goodness, here we go.
Robert Fulgate.
That's right, Robert Q. Fulgate. And so if you look him up, you'll find him to be very fascinating. He's I think one of the really cool things that he does or has participated in is the pushing of a spaceship to acquire 20% of the speed of light. Okay, so I don't know how fast that is, but it's pretty quick. And so they're kind of actually really figuring this stuff out, which is just kind of scary and exciting at the same time. What's also really kind of amazing is that Robert Q. Fulgate has in his spare time learned how to master the art of amateur astrophotography, and he's got some stunning images. So John Briggs will be bringing him on tomorrow night. You're going to want to watch him. We also have, of course, David Levy. David Eicher's going to be on talking about aluminum and barium. We have Jason. Oh, I'm losing some sleep here. I'm having a brain fog deal right now. I got up at 3 o'clock in the morning, folks. I'm sorry.
I'll help you with something here, Scott. 20% of the speed of light is 60,000 kilometers a second.
A second. Let's put that in miles per hour.
37,200 miles per second.
37,000.
And if you want to do it, if it's 37,200 miles per second, 37,200 miles per second.
Uh-huh.
And so you'd have to multiply by 3,600, right? To
Right.
get miles per hour, which is, oh my gosh, it's 133 million miles per hour.
That's just crazy.
Yeah, it's
Is that right?
it makes a journey to
Is that
Proxima
right? Yeah.
doable within a human lifetime.
Yes.
And of course, it depends on whether or not you're talking about on a nano-sized spacecraft, or you're talking about something big enough to hold people and supplies. You could get to Proxima in 20 years, give or take. I'd have to do the math.
Well, at 20% of the speed of light, we could actually measure, we could have people come back younger than the rest of us, I guess.
Yeah, exactly.
Right?
If one twin went off and flew for a year and came back
One of
for a
the
year.
Kelly astronauts took off on one of these things.
Exactly. The twin experiment could actually be done, which would be astounding And you could have somebody who would fly out and fly back and then be years younger than his or her twin.
Right.
Stunning,
That's pretty
stunning
stunning.
stuff.
Yeah. So we're
Um,
actually kind of doing science fiction stuff. So that's very
We
cool.
are. I mean, it would be. And
Yeah. Well, it's just all in the figuring it out, I guess. And then, let's
indeed,
make one of them and try it out, I guess.
I
So
love it.
we also have new people coming on, aside from Dr. Fulgate. We've got Lisa Ann Fanning. She is from the Royal Astronomical Society of Canada, the Halifax Center. So she's going to be on first time. We have familiar faces coming back on too. Caesar Brolo will be rejoining us after several weeks off. But some of the regulars will be on, Marcello Souza, and many of your favorites. So looking forward to that. And that will happen at 6 o'clock Central Daylight Time. Okay. So that's when it all kicks off. And we'll see how long it goes. The last one went till well after midnight here. So you just never know how long these things will go. But thank you very much to the audience for watching. And wanted to let you guys know that we have the advertisement for the Arizona Dark Sky Star Party will be appearing on the back cover of Sky and Telescope magazine. So you'll want to watch for that. I'll give you the issue that it's going to hit. I think it's the July issue. They work quite a ways out on these things, but or maybe it's the June issue. Not sure. But anyhow, and I'll be sure to share what it looks like and everything. So we went for simple, but kind of, trying to capture the moment. So thanks. And you guys keep looking up, and thanks for tuning in.
Thanks, everybody.
Next time.
Bye now.
Bye-bye.